start from the right, 1, and then go to famous 2, there's another carrying going on there, and then we add up the columns and carrying in the usual fashion. We end up getting that number there. Okay, so the carrying story really is, I guess, what makes this challenging for students. They have to learn how to do the carrying in the right way. And there's a lot of carries that are involved, especially with bigger numbers, and as I've said, it can get quite messy and maybe overly complicated if you have 2 very big numbers. Now, I wouldn't be surprised if many younger viewers regarded that previous kind of calculation with the multiplication as almost a dinosaur kind of activity. It's probably not something that you had lots of training in, because you based the calculators that were far from your fingertips. And so that whole procedure is maybe something that formally you are familiar with, but actually doing it practically might be a little bit of a challenge. And maybe some students have actually never really been taught this at all. Maybe some places, multiplication is just something that you do on a calculator. In that case, I think this Bexel way of doing things, which I'm not going to show you, provides an interesting alternative to the familiar one. One which I think is somehow conceptually easier to understand. It's easy to understand what's going on and why we're doing the various things that we're doing here in this approach where we're thinking about the numbers as being vertical rather than horizontal. So we take the same two numbers and regard them in a Bexel fashion. We'll multiply them as columns. So 15247, 15247, 93643, 93643. And what we do is very similar to what we did in that previous thing. So we're going to multiply this first column by 5. So let's see what it is. Take this and multiply by 3. And 3 times 7 is 21. 3 times 2 is 6. 3 times 5 is 15. 3 times 1 is 3. We're just writing down the various parts that are obtained and not doing any kind of adjustment. We're just writing down. Then when we move to the next digit here, the 4, we'll do exactly the same. Just multiply this 4 with all of these. We'll record all the possible parts. 28, 16, 8, 20, and 4. And then we multiply by 6, we'll get this column here. Each column is offset 1 down from the previous one. 6 times 7, 42, and so on. And then we multiply by 3, we get this column. And then we multiply by 9, we get 63, 36, 18, 45, and 9. Note that we haven't done any carrying. We are only concerned with multiplications between these various digits. And if you go back to the previous page, you'll see that each one of these multiplications has a multiplication that is there as well. Just that we typically included it with a carry from the previous one. We didn't write down explicitly, we only wrote down the rightmost digit. Here we're writing down all the possible parts. Now what we have to do is just add all of these things up horizontally. 21 plus 28 is 40, 6 plus 16 plus 42 equals 64. We add horizontally all the way down to 9. This is an answer. This is what the product of these two things is in our Vex 10 framework. But it's not in the standard extended form. So if in the standard extended form, we want each one of the digits to be between 0 and 9. That means we have to convert more than 10 things to one of the next one. So we take the 21 and we convert the 20 to 2 of the next type. So we only have one of these, and now we have 42 of them. We write down 2 and we take the 40 and convert them into 4 of the next type. So now we have 68 of these. We write down 8 and convert the 60 into 6 of the next type, giving us 74. So we write down the 4 and then convert the 17 into 7, giving us 117. We write down the 7 and convert the 110 that's left over to 11 of these. Then the 76 is 87. We write down the 7 and add 8 to here, giving us 47. We write down the 7 and add 4 to here, giving us 52. We write down the 2 and add 5 to here, giving us 14. We write down the 4 and add 1 to here, giving us a 1. So the carrying is all concentrated in this last step. And we convert each one of these into something that's just between 0 and 9 by converting the other ones using the exchange rules to those written down. And you can see we can do that in our heads in brief history. So this was a way for us to circumvent a lot of those carries that were distributed throughout the whole procedure in the last case. Now all the carrying is sort of concentrated at the end. Well, there's also a little bit of carrying as we add up these rows here. So when we added up these rows, we would of course also have to do a little bit of carrying. So we'll add up to get to 110, typically. Okay, so I'm saying that for multiplying big numbers by hand, especially if someone is not too proficient and hasn't spent a lot of time practicing, this is a much more reliable and simple method. So this is multiplication using our orientation. So do things horizontally, one column at a time, as we convert all the carryings at the end. And the number that we get is the same number that we got with the other method. So to summarize what we've done is we've introduced these Indo-Arabic numerals, which we're denoting by type num, which you can think of as standing for numeral now, and essentially base 10 vectors. Okay, and these are built up from our primitive natural numbers. So we assume we already understand our primitive natural numbers, and these vectors as objects are m sets of singletons, where a singleton is a list of one natural number. The arithmetic with these numerals is defined independently of our arithmetic with primitive natural numbers. It's not that we're just taking the prior arithmetic of natural numbers and just converting it into an arithmetic for these things. We're defining a new arithmetic on these guys, which is extending the arithmetic of natural numbers. It applies to numerals which are so big that they don't refer to actually any particular primitive natural number that we can write down. So our arithmetic is capable of dealing with numbers that have hundreds or maybe thousands of digits long. These numbers would be too big to actually represent primitive natural numbers. But nevertheless, they have independent arithmetic, which we have just been defining here. And the whole thing really rests on the vectoral arithmetic, or polynumber arithmetic, and these exchange rules that allow us to convert 10 of one level to 1 of the next level. The second one here, one has to verify that the arithmetic is actually well defined. That this exchange condition of changing 10 of these with 1 of these is actually well defined in the sense that the arithmetic is still independent of which of the various possible forms of the vectoral that we use. So we have a vectoral here and a vectoral here, we multiply them, and then we change the two vectorals by making various applications of exchange rules. We want to then convince ourselves that what we get is exchangeable with what we originally got, again, by just these exchange rules. So that's a great exercise for you to think about. And we see that the arithmetic with these numerals, these Hindu-Arabic numerals, is actually quite a lot more efficient than arithmetic with primitive natural numbers. That's the point and the beauty of the Hindu-Arabic system, right? It's a lot simpler than just working with strokes on a piece of bark. Much more efficient. And it allows us to deal with a lot bigger quantities. So if you have k digits available on a piece of bark, well, with natural numbers we can only get up to essentially k. But with these Hindu-Arabic numerals, we get up to essentially 10 to the k. So the possibilities for having a arithmetic with bigger numbers is vastly expanded. Now, Eric, this is important dictum that meaningful distinctions need to be maintained. Needs to be kept in mind here as well. So we're using these Hindu-Arabic numerals now in a number of different ways, and it's probably good for us to acknowledge these different ways that we're using them. So one way that we're using them is in an expression like this. We might write 34 is of type NAF. And that means that this 34 is our Hindu-Arabic shortcut for the primitive natural number given by this. So this is a primitive natural number consisting of a bunch of strokes, and we would express it as 1, 1, 1, 1, 1, etc. 34 times. And instead of writing this or saying 1, 1, 1, 1, 1, etc. 34 times, we'll allow ourselves to use our familiar Hindu-Arabic number, or numeral, to represent this thing. We'll talk about the natural number 34. We do want to be able to talk about the natural number 34 and write something like this. So when we're expressing a primitive natural number by a Hindu-Arabic expression, we're going to use this form. And this alerts us to the fact that we're actually thinking of a number of which is of type primitive natural number. As opposed to this usage, where we have 34 is an element of num. Okay, so 34 being a type of num is a shortcut for a base 10 vector. So here, the 34 is representing this base 10 vector, so it's a vector in the base 10 system. And I remind you that is really this thing here. Okay, so it's an M set of singletons with 3 zeros and 4 ones. So when we write 34 is a type num, we're really thinking in our minds that it represents this thing. When we represent or write down 34 is in NAF, we're thinking that it represents this thing. There's a big difference. And let's also note that actually we can go one level down because inside here, these things here are also natural numbers, but also in Hindu-Arabic form. And we could rewrite those just as primitive natural numbers. We can rewrite this 0 as this empty M set. And we can rewrite that 1 that's sitting there as the M set 1, which is the M set consisting of a single stroke. So if we're looking at 34 in the Hindu-Arabic numeral, then ultimately it really comes down to this somewhat formidable expression. That's just strips of all higher level things, and we're going right down to the level of things involving emptiness and somethings. So it's emptiness or nothing and something packaged up and presented in a simple data structure kind of way. I think it's useful to just compare our orientation here with some basic programming structure. So in the programming world, there are various levels of programs, and lower level programs and higher level programs. And so here's a kind of simplified view of that. So at the bottom, there's an actual machine that runs some hardware. And that machine typically is very simplistic at some level, maybe only dealing with zeros and ones ultimately. And then you have some machine language that's basically instructions that tells the computer what to do in terms of moving zeros and ones and changing them. And maybe then you have an assembly language, which is a little bit more sophisticated, but is another way of expressing or telling the machine what to do at the machine language level. And then there are these higher level languages where we have higher level constructs, things like C or Pascal or Basic or COBOL, which ultimately sort of generate assembly language stuff and have to be compiled and assembled and so on to eventually get the machine to run. And then there's other, maybe even higher level languages, maybe Java, Python, things like that. Okay, So there's a kind of a level of hierarchy, of sophistication and of power. But ultimately, to actually run, you have to kind of go down and actually tell ultimately the machine what to actually do. So unless you have some logical stream that ultimately goes down here and is consistent and correct, then your program is not going to work very well. So analogous to that, we're doing something a little bit in the same direction here. We're thinking about having a system of numbers which are based on something that's very elementary and perhaps simplistic. Basic dichotomy of nothing and something was, we said, sort of at the heart of things. That's sort of the essential building blocks. And from those things, we saw we could create natural numbers, and primitive natural numbers. And that's just one step up from the sort of basic hardware, basic dichotomy of nothing and something. And now we talked about these Hindu-Arabic numerals, or num. Okay, so we're at this higher level. It's using the primitive natural numbers, but it's more sophisticated, more complicated, but also more powerful, more efficient in some ways. And we might also then want to go higher up, because we also want to think about expressions that evaluate the numbers. Right, so far we don't have any way of talking about 8 to the 7, or 17 factorial, or 4 triangle 5, or any of these higher hyper-operations that we've been discussing. So this is then a natural kind of next realm to see, can we jack up our arithmetic with natural numbers from the level of Hindu-Arabic numerals to something more sophisticated, something more powerful, something that allows us to get at bigger and bigger numbers. Well, that's a very big challenge, actually. Okay? And I think it's fair to say that currently in modern mathematics, we don't have a proper theory of these things. But we do want to talk about the challenges involved in setting up something like that and the kinds of choices that we might make. So that's what we'll do in our next video. We'll talk about the possibilities for creating a type introduction of number expressions. We're looking for a way of working efficiently and consistently with arithmetical expressions that evaluate numbers. So I hope you're joining for that. I'm Noah Lover. Thanks for listening.
This last semester has been awesome. And now all that's standing in the way of graduation is final. And that means paper. Lots of paper.
Good day, I'm Noah Lover. We've been talking about the relationship between polynumbers and vectors, or vectors. And now we want to incorporate natural numbers, or particularly the Hindu-Arabic form of natural numbers, into the story. It turns out that fits very nicely. So we have a kind of convergence of several seemingly different kinds of objects, all somehow captured by essentially the same mathematical configuration. So that configuration is that of a vexel. And the vexel was a multiset consisting of singletons. And a singleton was a list of just one natural number. So usually we write a vexel like this, where we can see the singletons quite clearly. But in fact, a singleton like this is actually, if you look at it strictly speaking, something that looks like this. Okay, so here's the bracket outside there, but inside this too is actually the M set of unit marks contained there. So there's a mark and another mark. That's actually what natural number 2 officially is. So officially, this vector actually looks more like this. And it's useful to remember that it fundamentally has this almost very primitive aspect, just built up from our data structure point of view, from these essentially fundamental objects, these somethings, these unit somethings, or marks on the page. Now, this notion of a vector has an alternate formulation, or another way of representing it is in terms of a vector like this, where we record the multiplicities. We say there's 2 zeros, and 1 1, and 3 2s, 0 4s, and 2 5s. And then when we look at it like this as a vector, well, that's really almost the same as what we formerly called a polynumber, and wrote like this with a little bracket up on top. And that polynumber has another representation in terms of powers of alpha. It has 2 alpha to the 0 plus alpha plus 3 alpha squared plus 2 alpha to the 5th. So we have these various things which are all pretty well essentially the same thing. But I want us to think about the vectors as being primary. And it's really this thing here, this object here, which is the fundamental container, which is then being interpreted in a number of different ways. And in today's video, we want to extend that interpretation in a different direction to give us Hindu-Arabic numbers or numerals. The big advantage in regarding the vectors as primary is that then the operations become particularly simple to state, and their properties become relatively obvious. So addition of vectors is really just m-set addition, because vectors are, after all, m-sets. That's what we do when we add vectors. And multiplication is the m-set extension of this fundamental multiplication at the level of singletons, where the singleton n times the singleton m is the singleton n plus m, where here is the ordinary addition of these two natural numbers. So, for example, if we have this vector here, and this vector here, then here is the sum, and here is the product. Let's remind you, the product is obtained by taking all possible products between the elements of this one and the elements of this one. So this 0 times this 0 will be this 0. This 0 times this 2 is 2. This 1 times this 0 is 1. This 1 times 2 is 3. And similarly, again, another 1, 3 over there. Now, at the polynumber level, the same kind of thing would be written this way. This thing here would be the polynumber 1 plus 2 alpha, or maybe alpha 0, plus 2 alpha to the 1. And this thing here is just alpha to the 0 plus alpha squared, and then the corresponding multiplication is just the usual kind of polynomial multiplication, and it ends up being exactly the same thing as this one here. So this very simple multiplication of singletons really generates the polynomial arithmetic. All right, now we would like to add Hindu-Arabic arithmetic to the situation. And I remind you that our Hindu-Arabic numerals are thought of as independent of our natural numbers logically. There's a close connection, but we don't want to restrict our Hindu-Arabic numbers just to be representations of our primitive natural numbers. If we did that, then we would only have numbers up to 10 to the 200 roughly, and we want to have a wider range of numbers. So our aim is to try to find a separate framework for Hindu-Arabic numerals, and to have the definitions and operations and proofs of the operations which are largely independent of the natural number system. And we're going to take our direction from the parallel that exists between arithmetic with Hindu-Arabic numbers and arithmetic with polynumbers, or now also vectors. And that's illustrated with these two examples. Here we have an addition of ordinary numbers. 302 plus 47 is 349. And correspondingly over here we have the polynumbers 203 plus 74 equaling 943. Multiplication, we have, say, 423 times 12 is a familiar way of multiplying these numbers. 2 times 3 is 6, 2 times 2 is 4, 2 times 4 is 8, 1 times 3 is 3, 1 times 2 is 2, 1 times 4 is 4. And then we have to add them appropriately, 6, 7, 10 with some area and 5. And notice the parallel between that and multiplication of the corresponding polynumbers down here. Now, if we take 3, 2, 4, that polynumber, and 2, 1, and we multiply them, we also have the similar kinds of operations occurring. So 3 times 2 is 6. And this 7 occurs from adding 3 times 1 and 2 times 2. The 10 occurs by adding 2 times 1 and 4 times 2. And the 4 is 10 minus 4 times 1. So exactly the same products that we're having over here. We're having 6 products here. And there are also 6 products that we're figuring exactly the same 6 products. A slight difference is that over here, we're not compelled to carry. We don't mind adding 10 in that spot. We're not obliged to change that 10 into a 0 and add 1 to this 4 to make it 5. So in the vector world, we would not do that. But over here in the Hindu-Arabic world, we do that. So there is a parallel, of course, but there's also a big difference having to do with the carrying aspect, which is related to the fact that each one of these positions only supports the digits from 0 to 9, and nothing bigger than that. While over here, we're quite happy to have numbers which are bigger than 10 in any spot. All right, so there's a parallel, but there's also differences, and we want to understand the relationship between these two things, and ultimately we're going to define this world in terms of this world. Let's remind ourselves about this subtle but important aspect of carrying in our ordinary arithmetic. Of course, we know this based on having powers of 10. This 2 is 2 times 10 to the 0, here we have 0 times 10 to the 1, here we have 3 times 10 squared. And the crucial thing is that 10 ones equals 1 10. They're exchangeable, while 10 tens is the same as 100, and 10 hundreds equals 1,000, and so on. And that applies to each one of these positions, and it's kind of obvious because we have just powers of 10. So it's using this exchange convention really just underlines the fact that in the Hindu-Arabic system we end up only having at most 9 of any quantity in any position. We can check that digit up to 9, but no further. And so we can think about this if we like, going back to one of the earlier videos in the series, going back to primary school. We can think about having 17 $1 bills and 48 $10 bills. And what we're really allowed to do is to exchange, to convert $10 bills into